Okay, so our next example is find the integral of 3x minus 9 over x minus 1 times x plus 2 quantity squared. So first of all, let's just verify on top we have a numerator of degree 1, and on the bottom what we can see is that we're going to have a factor of x times two factors of x, which gives us an x times x in the first position, and that's going to give us a third degree polynomial, so the degree 3 polynomial on the bottom. We do in fact have a lower degree on the top than on the bottom. We can proceed with this method. So anyway, let's set this up. Let's just set up the decomposition. This is going to be a over x minus 1 plus b over x plus 2. Now, this is the thing that you have to recognize here, is that because I have what's called here, this is a repeated linear factor. It's not a quadratic factor because, even though x plus 2 squared is equal to x squared plus 4x plus 4, that's not an unfactorable quadratic. In other words, it's not irreducible. It can simply be reduced to x plus 2, x plus 2. But because the two factors are the same factor, and that's why we write this as x plus 2 squared, we actually have to treat it a little bit differently. What we would do is we write here c over x plus 2 squared, and that's going to equal 3x minus 9 over x minus 1 x plus 2 squared. Now I just want to emphasize one thing here. The rule for this is that you keep writing b over x plus 2, c over x plus 2 squared, d over x plus 2 to the third for all the possible factors, for all the possible powers of this repeated linear factor up to its highest exponent. So for example, if I had given, let's say, x to the 7th plus 5 over let's say x plus 1 to the 10th, the correct decomposition of this would be a over x plus 1 plus b over x plus 1 squared plus c over x plus 1 cubed plus dot 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 all the way up to, let's see, hij over x plus 1 to the 10th. So this is how you deal with a repeated linear factor. However many times it's repeated, you actually create one of these terms for all of the potential powers up to that highest power. So that's why I actually would need 10 different terms in here if I had x plus 1 raised to the power 10th on the bottom. Those examples obviously get very, very messy, which is why the ones we're going to do usually only go up to a power of 2 or maybe 3, but this is technically what the rule is. So now what we're going to do is we're going to multiply through by the denominator, just like we have in the past. That's going to give us a times x plus 2 squared plus b x minus 1 x plus 2 plus c x minus 1 is equal to 3x minus 9. So we're going to solve for, let me just put this off because that's not part of the problem exactly. So what I'm going to do is I'm going to solve for constants the same way that I normally have. I'm going to try to zero out certain factors and see if I can solve for constants. So let's let x equal 1. That's going to give us a times 1 plus 2 is 3, square that gives us 9, and then plus b, 0, plus c, 0, because I'm going to have factors of 0 next to b and c, so it doesn't matter what the other factor is. And then here I have 3 times 1 minus 9 is negative 6. So that gives us a equals, what I have is 9 times a equals negative 6, giving me a is negative 2/3. Let's do now, let x equal negative 2. So we see we have factors of x minus 1 and x plus 2, so the next natural thing to try is negative 2, because that's going to zero the x plus 2 factor. So this gives us now a times 0 plus b times 0 plus c times negative 3, and that's going to equal, I have negative 2 times 3 is negative 6 minus 9 is negative 15, so that gives me negative 3c equals negative 15, or c is equal to 5. So now what I need to do is I'd like to solve for b, but the problem is I've already zeroed everything that I can possibly zero, and for that reason, uh, I can't continue with this technique. I'm going to need some other technique. So let me show you two different ways that we can do this. Let's find way one. way number one to solve for b. And what this is we're just going to pick an arbitrary constant. So let's just, I'm going to, let's see, we'll say pick arbitrary value of x. So what I'm going to do here is I'm just going to let x equal 2. In other words, it doesn't really matter what I let x equal. I know what a and c are. I can just pick anything, and one way or another, I should be able to solve for the remaining constant. So let's let this be. We know that a is negative 2/3, so I can actually put that in here. Negative 2/3, and then I have 2 plus 2 squared is 16. And then b, we don't know, but b, that gives me 2 minus 1 is 1, and 2 plus 2 is 4, and then plus c, we know that c is 5, and 2 minus 1 is 1, and then 3 times 2 is 6, minus 9 is negative 3. So that gives me negative 32 over 3 plus 4b plus 5 equals negative 3. That, when you solve for the, if we actually rearrange everything, that's going to give us, let's see, 4b will equal 32 over 3. Let's put in the, let's convert everything to a fraction over 3. So I'm going to subtract 5 on the other side. 5 is equal to 15 over 3. And then we have negative 3 over 3, which is like negative 9 over 3. So that gives us 4b is equal to 8 over 3, and that gives us b equals 2/3. Write that a little neater. So that's one way that you can solve for b. It's not really my preferred way of solving for b. Let me show you what I think is the better one. Way number 2 is group by powers of x. And what you're going to see is that the coefficients of each power of x are going to have to match. So what we have here is, if I take, let's see, let's take a look up here at, I have a times x plus 2 squared. Well, we know that x plus 2 squared is just x squared plus 4x plus 4, and we also know that a is negative 2/3. So I have negative 2/3 x squared plus 4x plus 4. And then, I don't know what b is yet. I solved for it there, but I'm pretending that I didn't because I'm showing you a completely different way of solving for it. X minus 1 plus x minus 2, that multiplies out to x squared plus x minus 2. And then c, I have cx, well, first of all, we know c is 5, so 5 times x minus 1 is 5x minus 5, and that equals 3x minus 9. So what I want to do is I want to group all the x squareds, x's, and constants together. So first of all, let's look at what we have for x squared. I have x squared there and there, so that's going to have a coefficient of negative 2/3 plus b. And now let's do, in another color, let's do the x's. There we go. So now, the x's, I realize I usually put the x squared or the x at this on the right. I'm putting it on the left just because that's sort of the way I do this. This is going to be 4 times negative 2/3 is negative 8/3. I got that from here and here. And then plus b, which I got from there, and then finally plus 5. And then finally we're going to do the constant terms. What we can see are that we have negative 2/3 times 4 is negative 8/3. And then b times 2 is minus 2b. I got that from here and here. And then finally I have minus 5. So that's all the constants. In other words, the x to the 0 terms. And that has to equal 3x minus 9. So what I want you to do is look at this. Coefficients are going to have to match. I really only need one of these, but sometimes you're doing a bunch of them at one time, and it's easier if you just write out what all of these are, and then you get a whole bunch of little equations that you can solve. So what we know is that let's see, what we know is that there is no x squared term on the right, which means that whatever this is it's going to have to equal 0. Because otherwise we would actually see some sort of x squared term here, but we don't. So the only possibility is that the coefficient of x squared is 0. That makes it very easy because that means the only number that's going to 0 that coefficient is 2/3. So this is what I think is sort of the more satisfying way of solving for for the missing coefficients, is just to group them by powers of x and do them this way. So we now have the three coefficients that we need. What we can say is that the integral of 3x minus 9 over x minus 1, x plus 2 squared, is equal to the integral of negative 2/3 over x minus 1 plus 2/3 over x plus 2, and then plus 5 over x plus 2 squared dx. That's going to equal negative 2/3 ln x minus 1, and then plus 2/3 ln x plus 2. And then finally, this last term, if you do this, again, if you do it by u substitution, we could say u equal x plus 2 du equals dx. Then this integral becomes the integral of 5 du over u squared. You can, if you set it up that way, what you'll see is that this now comes out to negative 5 over x plus 2. So once again, it's not the case that the integral of 5 over x plus 2 squared is equal to ln of x plus 2 squared. That's not true. And you have to use u substitution to convince yourself that that's true. But here we have the answer to this problem. And let's see if we can get the whole thing on one page. There we go. Sorry, it's a little bit small, but there we go. That's how you solve this problem.